Physics is all very abstract, but often we can find analogies to help us understand the not so easy concepts. So I'm going to show you one of my favorite electric circuit similes. Not Smiles, Similes. But you are free to smile as much as you want as you watch this video, and after you finish it. Many students do not like electric circuits because they think circuits are, well, circuits. For me, an electric circuit is more like a river. The water flows in a circular canal over and over. The water molecules are the electrons. In a circuit, the electrons flow like water in a canal. So let's see, what other analogs are there between circuits and rivers? Electric current water speed. The electric current, or simply current, is analogous to the flow rate of water in a canal. This first simile is quite easy to understand. Water can flow very fast, and electric current can flow very fast too. Of course, all the molecules of water might not be moving in the same direction at the same speed, but there is average movement along the canal. Similarly, not all the electrons in the wire are moving along it in the right direction, but overall they are. Voltage, water height. Water that is higher has more potential energy. Even if you aren't a mechanical engineer, you know a column of water isn't going to stand there. It's going to fall down unless it's held by a dam. For circuits, electricity is going to flow from high voltage to low voltage unless stopped by, say, a switch that is off. Just as the difference in water height makes the water flow, a voltage creates electric current, unless it is stopped by a dam or switch. In the perfect world, water flows between the banks freely, but we are not in a perfect world. Our rivers have rocks in them. What are the rocks in circuits? Resistors. Bumpy rocks at the bottom of a canal can impede water flow. Resistors in a circuit can impede the flow of electrons, literally. However, there is one thing we need to understand. The water level lowers as it passes the rocks. Why? When water passes the rocks, it slows down. It's like the water behind the rocks is running into the traffic jam created by the slowing down of water, so the water piles up. The water that has made it past the rocks, however, can run along, so the water to the right flows away and lowers. Similarly, voltage decreases past the resistor. Capacitor dam. You may not have heard of a capacitor, but you definitely know what a water dam is. Even when water levels are different on the two sides of the dam, they can stay that way, allowing no water to get past, unless the difference in water height becomes way too big and the dam collapses. It may also be that water is flowing towards the dam, but eventually the difference in water levels will get big enough that water stops flowing or the dam collapses. For a capacitor, voltage around it is preserved, while no current can flow through it. There may temporarily be current flowing to it from one side and away from the other. The voltage will get large enough that current stops flowing, unless the voltage becomes so large the capacitor collapses. This phenomenon is used to simulate lightning. Inductor water mill. Let's analyze the effects of a passive water mill. It is not powered by energy and does not move on its own. The axle has no friction, but the mill has a large inertia. Side note here, the difference between friction and inertia is friction makes you slow down to a speed of 0, while inertia makes you stay your original speed. This means that the water mill tends to rotate at whatever speed the water is flowing. Normally it does not take energy to keep the mill rotating at its current speed since we do not have friction. However, if the water changes speed, then the inertia of the mill will impede the change in water speed because the mill does not want to speed up or slow down. If the water is speeding up, the mill will try to slow it down. However, since it's inertia, not friction, the energy used to speed up the mill will be stored in its rotational energy. And when the water slows down again, the mill ushers it to flow faster, releasing its rotational energy back on the water. So in short, the mill attempts to stop the water flow rate from changing. And the inductor? Easy. The inductor tries to stop the electric current from changing. When current increases, it impedes current and stores the energy in the magnetic field. When current decreases, it enhances current and releases its stored energy. Battery water pump. This is the energy source of the circuit and river. The pump's job is to lift the water on one side to a certain height on the other side, then stop. It's like a dam that also lifts water. If this water lifting dam were connected to a canal with rocks in it, it would create energy which is expended at the rocks. The water is lifted at the pump, lowers at the rocks because of reasons explained earlier, and goes back to the other end of the pump. If this water pump were connected to a regular dam, the water is lifted until the height is right and nothing else happens. The water level rises at the pump, is constant until the regular dam where it drops back. There's no more movement of water. Now the battery. Batteries are actually just voltage producers, so they are also called voltage sources, and increase the voltage by some amount. If a battery is connected to a resistor, the resistor expends the electrical energy created by the battery. Across the battery the voltage rises, and across the resistor the voltage drops back. If a battery is connected to a capacitor, the voltage across the capacitor increases until it equals the battery's voltage. Then there is no current. Now that we have the analogs of all the components of the circuit, we can easily find the analog of any complete circuit by connecting the components, like these. I'll apply our simile to an equation called Ohm's Law. Ohm's Law claims that when water is slowed down by rocks, the water speed, or current, is directly proportional to the water level drop, or voltage, and inversely proportional to the number of rocks in the river, or resistance. That is very easy to imagine. If we add rocks to the river, the water will slow down. If we use a bigger pump, the water will flow faster. Ohm's law is so easy now. I equals V over R. So now if you know the voltage and resistance, you can calculate the resulting electric current. So that's the end of our circuit similing, whatever. But there are also many other ways circuits are similar to other things. Yes, physics is packed with fun.